So our next section, our final section, 7.3, is titled Polynomial and Rational Inequalities. This section is going to look very familiar. This is going to look a lot like how we solved quadratic inequalities back in Chapter 4. So a polynomial inequality is any inequality where you can have a polynomial on one side and 0 on the other side of an inequality, either greater than or equal to, less than or equal to. So everything that we're going to do for the next few minutes will look like one of these, or will be able to be converted into one of these. We'll call these the standard form. We want to get 0 on one side. Alright, so first I would like to approach this by solving graphically. And I will say that we would like to solve x cubed minus 3x squared minus x plus 3 is greater than 0. So my first approach, just like with the quadratics, will be to graph the left-hand side and then find the pieces of it that are above the x-axis, that are positive. So, to graph this polynomial, we'll refer back to the techniques of section 7.1. We want to find the zeros and the end behavior and the multiplicity of the zeros. So, first thing I want to do is factor x cubed minus 3x squared minus x plus 3 so I can solve this equation. Alright. Now, one approach that we haven't used extensively with polynomials of higher degree, but which we can, is factoring by grouping. So I see I can get an x squared out of the first two terms and be left with an x minus 3. And then I see I can get a negative 1 out of the second two terms and be left with x minus 3. So ultimately, I can factor the x minus 3 out and be left with this factorization, which is almost complete. I can go one step further. This piece is a difference of squares, so I can factor it as x minus 1, x plus 1, x minus 3. So I see that my zeros are x equals 1, x equals negative 1, and x equals 3. And each of those has a multiplicity of 1. So I'll throw all three of those on my axis, and 1, negative 1, and negative 3. Now my end behavior, I have a positive leading coefficient and a degree of 3, so I'm going to be seeing something along these lines. So, knowing our multiplicities and our end behavior, I can tell my graph will look something like this. Now, my graph doesn't have to be amazingly accurate. If you would like, you can find your y-intercept just to make sure everything is where it should be. And if I do that, if I plug in 0 minus 3 times 0 squared minus 0 plus 3, I see that my y-intercept should be at 3, and here it's below the x-axis, it's negative. I've made a mistake. I forgot that this x-intercept was not at negative 3, it was at 3. So you can catch mistakes by verifying a little bit of additional data. My y-intercept should be at 3, so I'll plot that. And 1, 2, 3, there are my x-intercepts where they belong, and negative 1. My end behavior, and now my graph can hit the x-axis, crossing everywhere, and going up from there. Now, we see that the piece of the graph that we would like is the part above the x-axis. We want to be positive. So this piece is positive and this piece is positive, and that is happening to the right of 3 and in between -1 and 1. Now, we would like to be strictly above the x-axis, so the zeros, the x-intercepts, don't quite work for us. We would like our interval to be from -1 to 1, not including the endpoints, not including those x-intercepts. And there's a second interval that works for us, that piece from 3 onward, not including 3. And that is the solution to the inequality. Simple as that.